So today we're shifting our focus from horizontal kinematics, things that go from point A to point B horizontally, to vertical kinematics. And we're going to talk about free-falling objects. Okay, and what's different about free-falling objects? Okay. When we talk about free-falling objects, we still are considered to have constant acceleration, which means we can still use our kinematics equations that we learned, right? Vf equals Vi plus At, Vf squared equals V sub I squared plus 2A delta D. We can still use those kinematics equations because when you free fall, you still have a constant acceleration. Okay, so answer this question for me. Do lighter objects or heavier objects fall faster?
Heavier.
How many of you think heavier objects fall faster? Raise your hand if you think heavier objects fall faster. Okay, if I drop a light object and a heavy object at the same time, you think the heavy one's going to hit first. Raise your hand if you think that's true. Okay? Raise your hand if you think the lighter object will fall faster. Okay, raise your hand if you think they're going to hit at the same time. That is correct. Okay? They will hit at the exact same time, whether they are heavy or light. Okay? As long as we don't consider air resistance or we take air resistance out of the equation, we'll see objects that are shaped the same fall at the same rate. Now, if I drop a piece of paper that's flat and I drop a crumpled piece of paper, they're going to have different rates because one has more surface area to allow for air resistance. But if I drop two objects that have the same shape and roughly the same size, no matter what their mass, they're going to fall at the same rate. Okay? If you look at your kinematics equations, is mass anywhere in the equation? No. So that means mass has no effect on something's flight or something's path through the air. Okay, so we're going to watch a quick video. Constant acceleration for free-falling objects, we're still using A for our acceleration, but we're using acceleration due to gravity. Okay, and acceleration due to gravity is 9.8 meters per second squared. And I want you to go ahead and include a negative 9.8 meters per second squared in there. Okay, because gravity is always pulling in what direction? Down. Okay, and we're still going to use our coordinate systems here to think about positive direction, negative direction, things like that. So since gravity is always pulling us down, our A, or our acceleration due to gravity, in the vertical direction is always negative 9.8 meters per second squared. Okay, so that's always going to be your acceleration for objects in the vertical direction. Okay. Okay, whenever we have an object that's free falling, we've got to think about it in terms of constant acceleration. As it's falling, it's increasing in its speed. Okay? And it's increasing at a rate of 9.8 meters per second every second. That's what acceleration tells us. That acceleration due to gravity is negative 9.8. Don't forget that negative in there, otherwise your answers are going to come out really wrong. Okay? Because if you leave in positive 9.8, you're telling me that it's accelerating in the upward direction at 9.8 meters per second squared, which is incorrect. Okay? So we're going to go ahead and just dive in with some practice problems here. For these vertical kinematics problems, it's important that you draw a diagram to represent what's happening in the motion. Okay, it can be very simple, but as long as you understand what's happening, it's important that you draw a diagram. It's also important that you determine your coordinate system. You're going to determine where your origin starts. I always pick my origin for the motion, basically wherever the motion begins from. Okay, and I'll show you that here in just a second. So this says a ball's dropped from a tower that's 70 meters high. We're going to find out how far it will have fallen after 1 second, 2 seconds, and 3 seconds. We're going to find out how far down it has fallen. Okay? First thing that I want to do here is I'm going to draw myself a diagram. So my diagrams are very, very basic. Okay, here's my tower. I'm going to choose my origin, or my starting point, at the top of the tower, since that's where the motion begins. Okay, it's being dropped from the top of the tower. Does that make sense? You could choose your origin at the ground if you want. The only thing that's going to change there is your displacement. Okay, and let's talk about that for just a second. So basically, the ball starts here. It's going to travel in a straight path to the bottom. Okay, that's as simple as our diagram needs to be. Okay, so let's go ahead and start talking through what we know here. We know the height of this tower is 70 meters. The height of our tower is 70 meters tall. And since I chose my origin to be at the top of the tower, what does that tell me about my distance initial and my distance final?
Zero for distance final. Distance initial is 0, distance final is 7.
Good. Distance initial is 0 because I chose my origin to be at the start of the motion. Now, is my object going to end up 70 meters above where it started or 70 meters below where it started? Above or below? Below. So that means my distance final is negative 70 meters. Okay. Now, you could flip-flop these and make your distance initial 70 and make your distance final 0, as long as you are consistent in the way that you do that. I always choose to put my origin where the motion begins. That way my distance initial is about 99% of the time equal to 0. Okay, that way I know that my initial distance is 0, or my initial displacement. For my final distance, I look basically how far it's ending up from where it started, whether it's above or below. That determines the negative or the positive for my final displacement. Okay? Questions about that? Okay. What else can we pick out from this particular problem? What other variables can we pick out? Time. Okay, and our time is equal to what? This is 3 different questions here. It's asking us for after 1 second, 2 seconds, 3 seconds. So we're going to look just right now at the 1 second. Okay, so our time is equal to 1 second. That's asking us for 3 different answers, which means we do it in 3 different segments. Okay, we can't solve all of those at one time. This is 3 different questions. What do we know about our acceleration when we're talking about free falling? Yeah. Good. Our acceleration is negative 9.8. Okay, what do we know about our initial velocity? Initial velocity is 0 because it is dropped. That means the second it leaves my hand, it has no velocity yet. It's going to start increasing its velocity. Okay, now we need to make one little change. What's the question asking us for here? How far will it have fallen? Does that mean the ball's going to go all the way to the bottom? No, so that means our distance final can't be negative 70. Okay, distance final is really what we're solving for here. Okay, I want you to see that our distance final is going to be negative, but in this case, we're not letting it fall all the way to the ground, so our distance final is not 70. Okay, if our question was to ask us how far will it take for the ball to hit the ground, then our distance final would be negative 70. Okay, but here we're solving for distance final. Okay, is there any kinematics equations that we can use yet? First one, VF equals VI plus AT to solve for what? VF. Okay, we can do that. Do we need to? We can. We don't have to.
Why do we not need to find?
It's just asking us for final displacement, or final distance. So we don't really care how fast it's going at that time. We can use the second equation because it doesn't have velocity final in there. Okay, so Logan, it would work either way. You can still solve for final velocity after 1 second, solve for distance either way. Okay, so let's go ahead and use this equation. D sub F equals DI plus VIT plus 1/2 AT squared. Distance final is what we're solving for. Distance initial is 0. V sub I is 0. So our t squared is really 1 squared because we know our time. Okay, so that means our distance final is equal to negative 4.9 meters. Yeah? Okay, so this is telling us basically that we are now, after 1 second, we're 4.9 meters below where we started. Okay, so the ball has only fallen 4.9 meters. Let's go ahead and solve for how far it's fallen after 2 seconds. Okay, so what's the only thing in our equation that needs to change? Time. Okay, so d sub f equals 0 plus 0, 1/2, negative 9.8, 2 squared. Could we just take 4.9 times 2? I don't think so. Okay, it's because of that t squared that we can't just multiply it by 2. Okay, so don't try to take shortcuts. So after 2 seconds, it's fallen a distance of how many meters? Negative 19.6. So at 2 seconds, it's fallen almost 20 meters below where it started. 19.6. Okay, and our last time is going to be 3 seconds. We're looking at the same situation here, but we're going to say, suppose the ball from the last problem is thrown downward with an initial velocity of 3 meters per second. What would its position be after 2 seconds? Okay, so we have the same situation. We still have our tower that's 70 meters tall. We still have a ball that's going in the downward direction. But this time, instead of dropping it, we're throwing it down. So what variable does that change for us? Initial velocity, good. And what does that make our initial velocity? Negative 3 meters per second. And why do we think it's negative? It's going down. So once we start working with these kinematics, we've got to start thinking in terms of direction. The negative indicates to us a direction. If I said I was throwing 3 meters per second and I didn't include the negative, that means that I'm throwing it upward at 3 meters per second. It would have to reach its peak height and then begin to fall. Okay? Nope. Nope. So here we've got to pay attention to anything that's going down has to have a negative direction. Anything that's going up has to have a positive direction. So that's something you've got to be very, very, very conscious about. Okay, what else do we know? We know time, which is 2. We know acceleration, which is equal to negative 9.8. Good. And what are we solving for? D sub f. What is our initial displacement? 0, because I put my origin right up here at the top. That's the reason I put that little cross, okay? That's telling me that's the crosshairs of my origin or my axes, okay? That's telling me that my origin is going to be at the top where the motion begins. Okay, and it's important that you do that as well, that you indicate to me where the origin is. Okay, what equation can we use? Same one we've been using, right? D sub f equals 0 plus, this time can our second term be 0? No, because we have an initial velocity. We have an initial velocity. So we're going to take v sub I, which is negative 3, times time. Okay, so this is VIT plus 1/2 A times t squared. So if we compare this to the object that's dropped at 2 seconds, have we fallen a farther distance or a shorter distance? Has the ball fallen farther or not? Yeah. Does it make sense as to why it has fallen farther? We threw it. We gave it an initial velocity in the downward direction. Okay, so after 2 seconds, it should make sense to you that it's traveled a further distance because it started with an initial velocity. Okay? Questions on this one? Does the math we're doing change at all when we talk about vertical? No. Only thing that changes is that you always know your acceleration, so that takes out a step of having to solve for acceleration, and you have to pay more attention to positive, negative distance or displacement. Okay. Okay, person throws a ball upward into the air with an initial velocity of 15 meters per second. Calculate how high it goes and how long the ball is in the air until it reaches his hand again. Okay, so here's my diagram. This ball is going to go up in the air, reach its peak height, and come back down. So here, where would the origin of this motion be? Huh? Right where I throw it from. Okay, so it's my hand. The origin of my motion is the hand. The second that it becomes a free-falling object, that's where our motion begins. So wherever I released it from, that's my origin right there. Okay? Uh-huh. So we've got a couple different things to work with here in this problem. First of all, we're going to calculate how high it goes. Okay? That means we're solving for what variable? We're solving for distance final, but we're only looking at it to its peak height. Okay? We're looking at distance final basically from my hand to its peak height. Okay? So let's talk through the variables that we know here. We know our initial velocity, right? And it's equal to 15. Is it positive or negative? Positive, because we're throwing it up. Okay, positive. That's all that it tells us. What else do we know? We know acceleration, good. Negative 9.8. What else do we know? D sub I, good. And it is 0. And we know one other thing. Nope. Good question, but acceleration is still pulling it back down. Okay, so acceleration is still pulling down. So Logan asked, would our acceleration be positive since we're throwing it upward? Acceleration due to gravity is always in the negative direction. Always, always, always. It's always pulling it back down. Velocity final is 0. Why is velocity final 0? It's at its peak height. Okay? If we're only looking at something to its peak height, that means at its peak height or when it reaches its highest point, its velocity is 0, just for that little millisecond. So that's what we're looking at here. And we're going to solve for d sub f. What equation can we use? The third one, because we don't have what variable? We don't have time. So let's use the third one, which is vf squared equals vi squared plus 2a df minus di. Okay, we know our velocity final. So all we're looking at here is the first half of the motion. Okay, we're looking at from its release point to its peak height. First half of the motion. So 0 squared equals 15 squared plus 2 times negative 9.8 times df minus 0. Okay, so mathematically, we're going to square that 15 first and get 225. So we'll have 0 equals 225 minus 19.6 df. What do we do with the 225? we need to subtract it over to the other side. Subtract it first. It does not have a variable attached to it. So we need to subtract it to the other side. So negative 225 equals negative 19.6 df. And that gives me a final displacement of 11.48 or 11.5 meters. Its peak height, it's going to travel 11.5 meters to its peak height. Now we need to solve for time on its way up and on its way down. There's two different ways you can go about solving for time. Okay? The first way, and I think the simplest way, is to solve for time to peak height. Find out how long it takes for it to reach its peak height, and then we can multiply that time by 2. Okay? And this is why. When something reaches its peak height, it's going to have the exact same path on the way down. Okay? So that means it's going to take just as long to come down as it did to go up. Okay? So if we find our time to peak height, we can multiply that by 2, and that'll give us the time for our total motion, all the way up and all the way down. Does that make sense? Yes or no? Okay. All right. Let's do it that way then. Okay, so we're going to solve for time. At peak height, at its highest point, we know that velocity final is equal to 0, right? We already talked about that. So what equation can we use to solve for time? We can use the easy one. Yep, the very first one. So VF equals VI plus AT. Okay, so VF is equal to 0. VI is equal to 15 plus negative 9.8 times time. However, if you choose to solve this way, you cannot stop right here. Okay, you cannot stop right here because this is only the time it takes for it to reach its peak height. Okay, that's only on the way up. It's not on the way down. So to solve that, we just multiply it by 2 because it's going to take the same time on the way up that it does on the way down. Did we all get 1.53 first of all? Yeah. Okay, good. So that means our total time is equal to 3.06 seconds.